Alright, we're going to go over 9.7, which is dealing with inverse trigonometric functions. And really what you need to be doing from this section is just to be memorizing the fact that these inverse trig functions have to be restricted. The domain is to a point cut off and restricted to a certain interval. And then same thing with the range. So we'll be talking about what those cutoffs are. Alright, remember, I just want you to recall logarithms and exponentials, and I just want you to remember that when we were dealing with these, what would happen is the x and y roles would reverse. So in that case, when we would graph something, here would be an example of exponential growth. Right, that's just a sketch of what this would look like. Then what I want you to remember is that when we graphed the inverse function of 2 to the x, which is, of course, the logarithm base 2 versus the exponential base 2, what would happen is it would look something like this. It was kind of like this graph right here, but flipped over the y equals x line. So what happens is this kind of to a point lays on its side, or it flips over and lays on its side. I want to bring up this as well. This is just the typical function y equals x squared, so it's the most basic quadratic. And does it pass the vertical line test? Yes, it does. So it's a function, right? That's what it has to be a function. When you look at it and draw a vertical line through it, it can only have one output. For every x value, there is only one y value. So one y value for every x. Alright, does it pass the horizontal line test? No. So if you drew a line and you looked at it and how many times it crosses that horizontal line, you can see here it crosses 2. That means if we were to draw the inverse function, remember, keep in mind that we're going to have something where these x and y values reverse roles. So we're going to have, oops, sorry, bad drawing. But here it is. It's that parabola that's been turned kind of on its side. So now what that states is if we were to take this and pass if it didn't pass the horizontal line test, then it's not going to pass the vertical line test when you flip it on its side. So therefore this one does not have an inverse function because it's not a function. It doesn't have one y value for the every x value. It has two y values. So I'm going to go ahead and erase this real quick. Alright, so it does not have an inverse function. However, we can do something such as restrict the domain to being just x values that are greater than 0. If that's the case, that takes away this portion of it, and now not only does it pass the vertical line test, but it also now passes the vertical line test when we take away and restrict that domain. So now we could go ahead and say that this does have a inverse function. So I just want you to consider the graph of sine of x. First of all, let's consider the function sine of x. You've seen my picture before, and this was just my crazy doodle. So remember, trig functions input angles, whether they're in radians or degrees. So here my sine function is inputting the angle pi 6 radians. It works its little magic, and then what happens is they output side-to-side ratios. So sine, once again, is opposite over hypotenuse. You would look at the angle, look at the right triangle that it forms, and you would look to the opposite side and then put that over the hypotenuse. So then we have what we call inverse trig functions, which are also notated as arcsine or sine to the -1. But what that will do is it will take the work of our sine function, it will take the output, so these side-to-side ratios, it will work its magic. But here is a little flaw in our story because sine to the -1 of x, or arcsine, has a problem. What is the problem? What's the problem? Well, let's consider sine inverse, and then it's taking in that 1/2. What does that equal? Well, if you look on your unit circle, remember, it's the opposite of what we were thinking. Before we would look to an angle, one particular angle, and we would say, well, what's its opposite over its hypotenuse on the unit circle? And being that the unit circle has radius of 1, then we were really just looking at what's the opposite or the vertical movement. So the issue now is we're looking at the vertical movements of 1/2. What angles have the vertical movement of 1/2 on our unit circle? And here we can see, well, it's 1/2. Heights would be this point on the unit circle and this point on the unit circle, which happens to be, of course, pi sixths. But it also happens to be 5 pi sixths. So this is a problem because, I mean, which one is it? Arc sine, there's confusion as to what is the possible outputs. And once again, in order to be a function, we can only have one output for every input. And not only that, but I could go around the circle again. So pi sixth plus 2 pi would also be another solution for something with the height of 1/2. And not only that, I could go around as many times as I wanted. Same thing with this 5 pi sixth. I could find out coterminal angles with it just by wrapping around the circle and ending up in that same exact spot again and again. So there are multiple answers for this. So recall, for a function to have an inverse, it must be 1 to 1 and pass the horizontal line test. So let's look at that function of sine. Yes, it passes the vertical line test. You could draw many vertical lines in here, but it does not pass that horizontal line test. Okay, there's many hits on this horizontal line test, which means it would be a problem if we wanted to try to graph the inverse sine. However, what we do is we restrict this sign just like I did in that other slide. I'm going to restrict it to just being from, here is negative pi halves to pi halves. Okay, we're just going to restrict it there because after that point what would happen is it would start to repeat and it wouldn't pass the horizontal line test. So we're only looking at answers on, and I will sketch this real quick, on this side of the unit circle. That's only where our outputs can be from an inverse sine function. So let's look at that one sine inverse of 1/2 again. Well, because we've eliminated the fact that it cannot be on this side of our unit circle or anywhere over here, what's going to happen is we do have a defined output now. It's just that pi sixths. Okay, so no more confusion because we restricted the domain. Okay. Just a few things that I want to run through, and then I'm going to be doing examples. I'm going to breeze through these next few slides. Because we restricted the domain, what's going to be happening here is we can only have values from -1 to 1. So if I ever try to do this to you, arc sine of, and Hannah, you actually brought this up. If I did like 3/2, for example, what you're going to get is an error on your calculator because this is not within our domain. We can't possibly do an arc sine like this. So that was a really good observation. The other thing is, once again, you can only have output values that are in this interval. So once again, that is restricted to one side of the unit circle. So one example is, of course, this one that we just did. And once again, I have to just show you that it could have been, I mean, technically, when we would ask ourselves, this is asking what angle, we're looking for an angle because remember, arc sines and inverse trig functions output angles. They take in side-to-side ratios, output angles. We're asking ourselves what angle would have a height or a y value of 1/2, and because there were two possible answers, this restriction limited it to only this part of the unit circle, so we're only interested in pi sixths. So this is two ways that they can notate it in your book, just so you know they're both inverse sines. Alright, inverse cosine, what they do is they restrict it to this section right here. So cosine is the one that's a little bit different. Cosine is going to be just looking at from 0 to pi. So this is the part of the unit circle that you're looking on for arc cosines. And I'm going to kind of breeze through this because I want to just get to examples. You can look over this if you want to. But once again, we have that whole restriction thing going on. And then finally tangent, we're going to restrict it. Once again, it does not pass the horizontal line test, so what we do is we cut some things off, and we're only going to look at from -pi to pi again. So cosine is the odd one out. What we're looking at is just this side. So how does this all play into, or how does this all go into play? I'm going to go ahead. You can pause it on here if you want to kind of look this over. Hopefully this is making sense based off of our analysis of sine, arc sine, I should say. Alright, so we're going to do some examples from your book. I'm going to look at number 7 and 9. Okay, so here I'm trying to solve this inverse trig function, and what you'll end up having to do is look at your unit circle, and this is the thing. Remember, arc cosine is only specifically looking at one portion of that unit circle, and it's the odd one out. It's only looking at the top in the top two quadrants 1 and 2. So you're asking yourself, which angle has this x value of negative the square root of 3 over 2, and remember that's that red flag that it's that longer side of that special triangle. So we're looking at this, right, oops, bad triangle, but oh man, this triangle right here. So here's the square root of 3 over 2, and we knew we had to go in the negative direction. So technically we could have had another triangle down here. But once again, because we're restricted to the top portion of our unit circle, we're looking at this angle right here. And this angle happens to be on the unit circle pi by pi sixths. Alright, so what we just did was you have this input of negative square root of 3 over 2. You get this output of an angle, specifically applying to that unit circle. Number 9, arc tangent. Alright, arc tangents are a little bit trickier to do, because when you're trying to find angles with this ratio, side-to-side ratio, unfortunately it's not like cosine where I could just say, okay, I'm looking for the angle with this x value as its x value, or yeah, of that coordinate point. Unfortunately for tangent, you actually have to kind of calculate these and say which angle, when I calculate the tangent of it, will get me negative square roots of 3. So for arctangent, being that cosine was the odd one out, it's like arctangent is like arcsine. We're looking at this portion of our unit circle. It's quadrants 1 and 4. So I'm just going to go ahead and understand that I am looking down in the negative range. All of these tangents would have a positive divided by a positive side-to-side ratio, because it's a positive x and a positive y. I know I'm going to be looking down here. So I also know that it's not that 45-degree angle, because the 45-degree angle of tangent is going to just be, it's that square root of 2 over 2, comma the square root of 2 over 2, and when you take that, they're just going to be equal to 1 when you take the ratio of the x and the y. So I'm going to be specifically looking at these two, and I'm going to guess this one. Okay, so when I guess this one, actually, you know what, I'm sorry, I'm just going to guess the one that I know it is, and it's because I've done these enough that I know it's going to be this. But let's go ahead and look at this triangle. We go over 1/2 down, over 1/2 down the square root of 3 over 2. So that should be negated. And I'm going to take the opposite, which is the y value, over the x. So remember, tangent of an angle is equal to the y over the x value, or the sine over the cosine. So when I calculate this out, I'm trying to find out what angle, trying to find out this angle right now. What angle would give me the tangent of this? So tangent of theta is equal to, in this case, the square root of 3 over 2 divided by 1/2, which is the same thing as multiplying by 2 over 1. This was negative, sorry. So those cancel out, and ta-da, there we go. So we just found the angle. It's this special angle right here. So the arctangent, I'm going to cross this out, is equal to, what is that? Oh goodness, what is that? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 10 pi sixths, which is equal to 5 pi thirds. It's that special angle on your unit circle. I'm also going to do number 49. And 49 looks like this. Sine 3/4. Okay, so what's happening is they say make a sketch of the right triangle. This is really understanding that you're looking at an arctangent of 3/4, so you get really an angle. You're going to be observing a certain right triangle with a certain angle, and then you're going to be taking the sine of that particular angle of that certain triangle that you constructed. I hope that made sense. But I'm going to do it. So arctangent of 3/4. I know that I'm going to be looking at an angle, and I do know that arctangents are specifically looking at these two quadrants. So I'm going to specifically be looking at something like this with a opposite of 3 or a height of 3, and then the length of the x value of 4. So this is the angle that I'm looking at. It's the triangle specifically associated with this arctangent of 3/4. So there is the theta. So now I want to find out, well, what is sine of this theta of this particular triangle that I've constructed based off of this information. So I do need opposite over hypotenuse. I will have to calculate my hypotenuse. This is a 3, 4, 5 triangle. It's one of those special cases. Otherwise, you could always do 3 squared plus 4 squared and then square rooted, and then you get their 5. So in this case, what I'm looking at is sine is going to be 3/5. That is your final answer. You went from finding out an angle, right, getting an angle out of this, and then observing from that angle what is the sine of that angle. So there we have it.